Welcome to the second part of our AI literacy journey: machine learning, deep learning, and generative AI. Artificial intelligence isn't magic, it's powered by systems that learn from data. Machine learning is the foundation, where algorithms find patterns and make predictions from experience. Deep learning takes it further, using layers of artificial neural networks inspired by the human brain to recognize images, speech, and complex behaviors. And then comes generative AI, models like ChatGPT, DALL-E, and others that can create new text, images, music, and even code. Instead of just analyzing data, they generate new content, reshaping how we work, learn, and create. In this section, we'll explore how these technologies work together, why they matter, and how they're transforming industries around us. According to the official text of the Act, an AI system is, and I quote, a machine-based system that is designed to operate with varying levels of autonomy and that may exhibit adaptiveness after deployment, and that, for explicit or implicit objectives, infers from the input it receives how to generate outputs such as predictions, content, recommendations, or decisions that can influence physical or virtual environments. That's a dense legal definition. So let's unpack it into four simple key ideas. First, it's a machine-based system. This means we're talking about software and sometimes hardware, not a simple static set of instructions. Second, it operates with varying autonomy. It can function without constant human control, ranging from systems that assist us to those that can act fully on their own. Third, it can be adaptive. A crucial part of the definition is that the system can learn and change its behavior after it has been deployed into the real world. And fourth, and most importantly, it infers to generate outputs. Its core function is to deduce patterns from the data it receives. It doesn't just retrieve a pre-written answer. It figures out how to generate new predictions, content, recommendations, or decisions that can have a real-world impact. So, what does this mean in practice? This broad definition is designed to cover everything from machine learning models used in finance or healthcare to generative AI like chatbots and image creators, and even autonomous robots. Conversely, it is designed to exclude simpler software. A basic calculator or a straightforward spam filter that uses a fixed list of keywords would generally not be considered an AI system under this law. In summary, the EU AI Act defines an AI system not by a specific technology, but by its core capabilities: the ability to infer, to act with autonomy, to adapt, and to generate influential outputs. This ensures the regulation can stand the test of time, focusing on what these systems do rather than how they are built. Managing artificial intelligence systems is not a one-time event, but a continuous journey. From the first spark of an idea to the final day of retirement, it demands rigorous governance and unwavering oversight. This is the core of our comprehensive framework for the AI system lifecycle. Our approach ensures that every AI system remains ethical, effective, and accountable at every step of its existence. We achieve this through a structured 5-stage lifecycle, where each phase has its own critical requirements and clear responsibilities. This framework bridges two essential domains: organizational governance, the rules, culture, and structures of your company, and use case specifications, the unique details of each AI application. At every single stage, we clearly define the designated actors. We answer the critical question: who is responsible for meeting these requirements? And we mandate the supporting evidence to prove it. The framework is designed to be completed in a logical chronological sequence. The most intensive diligence and reporting requirements are intentionally concentrated in the early stages. This is because the foundational decisions made at conception and design ultimately determine the system's long-term performance, ethical footprint, and overall success. In essence, this framework treats governance as a dual imperative. It is both an organizational mandate and a use case-specific necessity. This ensures that ethical considerations and technical excellence do not compete, but advance in tandem throughout the entire operational life of the system. Building a successful AI system isn't just about the model itself. It's about the environments where it learns, is tested, and ultimately operates. These are the three critical environments that guide an AI from development to real-world impact. First, we have the training environment. Think of this as the AI's classroom and library. It's a controlled, isolated space composed of carefully prepared datasets, the training data for learning, and the validation data for initial checks. Here, the model studies vast amounts of information to learn patterns and relationships, all without being exposed to the unpredictability of the real world. This isolation is crucial for building a strong foundational knowledge. Next is the testing environment. If the training environment is the classroom, this is the final exam hall. It's a separate, secure space that contains a special set of data the model has never seen before, the held-out testing data. This is where we conduct an unbiased evaluation of the model's performance. We test its ability to generalize, ensuring it has truly learned the underlying concepts and not just memorized the training material. Passing this stage is a non-negotiable gate before any deployment. Finally, we have the production environment. This is the real world. It's the live setting where the fully trained and tested model is deployed to make predictions on new, incoming data. This is where the AI delivers actual value to users and stakeholders, powering applications, informing decisions, and interacting in dynamic, real-time conditions. It's the ultimate test and the reason for all the previous stages. Understanding and maintaining the separation of these three environments is a cornerstone of responsible and effective AI development. Welcome to Stage 1, the design phase. This is the foundational stage where we lay the groundwork for a successful and ethical AI system. The primary goal here is to prevent a critical failure mode known as problem misspecification, which occurs when the problem we define and build for doesn't actually reflect the true underlying challenge we need to solve. To avoid this, we focus on 4 key activities. First, we formulate the use case. This is where we move from a vague idea to a precise definition. We ask, who are the stakeholders? What is the exact problem scope? And how will an AI system specifically solve it? We also identify existing solutions to understand the landscape and set clear, unambiguous success criteria. Second, we define the metrics. How will we measure success? We establish 2 families of metrics from the very start. One is robustness metrics, like accuracy and precision, to measure technical performance. The other is fairness metrics, such as demographic parity and equalized odds, to ensure the system's outcomes are just and unbiased. Third, we assess the AI fit. This is a crucial reality check. We must critically evaluate if AI is truly the optimal solution for this problem. This involves choosing the right project archetype. Will the AI improve an existing process, augment a human-driven one, or fully automate a task? Each path carries different implications and trade-offs. And fourth, we conduct a comprehensive risk analysis. Before a single line of code is written, we proactively assess potential risks. This includes operational risks of failure, security risks of interference, and legal risks of non-compliance. Techniques like failure mode and effects analysis, or FMEA, are used, and we pay special attention to evaluating potential impacts on fundamental human rights. Getting the design phase right is our most effective strategy for building AI that is not only powerful, but also responsible, fair, and aligned with our true objectives. We now move to Stage 2, the development phase. This is where our plan from the design stage meets reality as we build and refine the AI model itself. This phase is a structured, iterative process with several key steps. It all begins with Step 1, sourcing the data. This is the foundational step. We extract, transform, and load data from multiple sources, creating our initial dataset. Crucially, we must ensure this process complies with regulations like GDPR and CCPA, and that we have obtained proper permissions for the specific use case. Step 2 is to prepare the data. Raw data is rarely ready for training. We apply critical techniques like vectorization for efficiency, normalization to put features on a common scale, and carefully handle any missing values. Finally, we strategically split the data into three distinct sets: for training, for validation, and a final holdout set for testing. Alongside this, step 3 is to analyze the data. We must understand what we're working with. This involves analyzing data distributions, proactively identifying biases, and rigorously testing for data quality and integrity. We document our assumptions and validate the data against all schema requirements to ensure it accurately represents the problem we're trying to solve. Step 4 is the core of development: training the model. Here, we establish a baseline performance using common, well-understood algorithms. We apply feature engineering to improve performance, but we must do so carefully to avoid injecting our own experimenter bias into the model. Finally, step 5 is an iterative cycle of validation and tuning. We continuously measure the model's performance on the validation set and adjust its hyperparameters. The goal is to find the optimal balance, navigating the fine line between underfitting, where the model is too simple, and overfitting, where it memorizes the training data and fails to generalize. This entire development phase is a cycle of building, measuring, and learning, all focused on creating a robust and effective model ready for rigorous evaluation. Now we enter stage 3, the evaluation phase. This is our final quality gate before a model goes live, where we conduct a comprehensive performance assessment to ensure it is both robust and fair. This phase consists of two critical pillars of testing. The first is robustness testing. Here, we put the model through its paces. We calculate its performance on the held-out test dataset it has never seen. We compare training versus testing metrics to diagnose issues like overfitting. Crucially, we go beyond numbers by visualizing the model's predictions to identify any systematic failures that raw metrics might miss. The ultimate goal is to verify that its performance meets the predefined benchmarks we set during the design phase. The second, equally vital pillar is fairness testing. An accurate model is not enough. It must also be a just one. We rigorously evaluate discrimination metrics across protected groups, testing for problems like disparate impact and unequalized odds. If biases are detected, we apply post-processing corrections and carefully document all fairness trade-offs and the decisions we make to address them. This comprehensive assessment informs a critical developer decision: to refine the model further or to proceed. Once a model passes these tests, we move to deployment. This is the strategic release into the production environment. It involves defining how the model will be served, for instance, as a REST API, and assessing the impact on user privacy and security. To minimize risk, we strongly advocate for pilot approaches like canary deployment, which gradually introduces the system to a small portion of production traffic. This allows us to monitor real-world performance and catch any unforeseen failures before a full rollout. The evaluation phase ensures that we deploy AI systems that are not only powerful, but also dependable, fair, and ready for the real world. The operation phase. The launch of an AI system is not the finish line. It's the beginning of a continuous cycle of monitoring and improvement. Our work here ensures the system remains healthy, accurate, and valuable over time. This phase is built on 4 key pillars. The first is monitoring performance. We proactively track key statistics, watch for shifts in data distribution, and observe how users interact with the system. Every issue and the actions taken to resolve it are meticulously logged. This is our early warning system for detecting model decay. The second pillar is collecting feedback. We gather insights both implicitly from user behavior and actions, and explicitly through direct channels like surveys. We then classify any errors to understand their root cause. Are they due to user input, a system flaw, or a misunderstanding of the context? The third pillar is managing regular updates. Model decay is not a matter of if, but when. As production data evolves, the model's predictions can degrade rapidly, sometimes in days for dynamic use cases like fraud detection. To combat this, we define strict retraining schedules, choosing between manual updates or continuous learning to keep the model relevant. The final pillar is problem resolution. We maintain detailed records of every issue, the solutions applied, and their effectiveness. This creates a knowledge base for future improvements. We establish clear ownership for fixes and rigorous testing protocols for all updates, ensuring that each change is both safe and effective. In the operation phase, vigilance is our greatest asset, ensuring our AI systems deliver sustained value long after their initial deployment. We now arrive at the final stage of the AI life cycle, Stage 5, the retirement phase. Even the most well-designed AI systems eventually reach their end of life, and responsible decommissioning is crucial to minimize disruption and protect sensitive information. This phase involves two critical actions. First, we must assess deactivation risks. This means carefully evaluating the impact of shutting the system down. We look at potential service disruptions for customers and examine all internal system dependencies. For AI and safety-critical applications, this assessment is paramount, as a poorly managed retirement could itself create significant hazards. Second, we must handle AI residuals. An AI system is more than just a model. It's the data, code, and logs it leaves behind. We must make deliberate decisions about what to do with these residuals, including training data, stored predictions, source code, and firmware. This involves determining what must be retained for legal or compliance reasons, and what must be securely disposed of based on security and environmental policies. Finally, when retiring a system to upgrade to a new one, the goal is a seamless transition. We carefully deactivate only the impacted components while ensuring continuous service and a smooth migration of essential data. The retirement phase closes the loop on the AI lifecycle, ensuring that our systems are not only built and operated responsibly, but are also concluded with the same level of diligence and care.